Differentiation and integration as inverse processes. We now bring together the two parts of the fundamental theorem. We regard part 1 as a fundamental because it relates integration and differentiation. But the evaluation theorem from section 5.3 also relates integrals and derivatives. So we rename it as part 2 of the fundamental theorem. So the fundamental theorem of calculus. Suppose f is continuous on a closed interval from a to b. Number 1, if g of x is equal to the integral of f of t dt from a to x, then g prime of x is going to equal f of x. Part 2, the integral from f of x dx from a to b is equal to f of b minus f of a, where f is any antiderivative of lowercase f, that is, f prime of f is equal to f. We noted that part 1 can be written as d with respect to x of f of t dt from a to x is equal to f of x, which says that if f is integrated and then the result is differentiated, we arrive back at the original function f. So therefore in section 5.3, we reformulated part 2 as the net change theorem. So f prime of x dx from a to b is equal to f of b minus f of a. This version says that if we take a function f, first differentiate it, and then integrate the result, we arrive back at the original function f, but in the form of f of b minus f of a. Taken together, the two parts of the fundamental theorem of calculus say that differentiation and integration are inverse processes. Each undoes what the other does. The fundamental theorem of calculus is unquestionably the most important theorem in calculus, and indeed it ranks as one of the great accomplishments of the human mind. Before it was discovered, from the time of Eudoxus and Archimedes to the time of Galileo and Fermat, problems of finding areas, volumes, and lengths of curves were so difficult that only a genius could meet the challenge. But now, armed with the systematic method that Newton and Leibniz fashioned out of the fundamental theorem, we will see in the chapters to come that these challenging problems are accessible to all of us. Now, proof of the fundamental theorem of calculus 1. Here we give a proof of part 1 of the fundamental theorem of calculus without assuming the existence of an antiderivative of f. We're going to let the function g of x equal the integral of f of t dt from a to x if x and x plus h are in the open interval from a to b. Then we would say that g of x plus h minus g of x is going to equal the integral from a to x plus h f of t dt minus the integral of a to x f of t dt. And so therefore, we can say that the integral from a to x f of t dt plus the integral of x to x plus h f of t dt minus the integral of a to x f of t dt. Well, what happens here is that we can see that this integral on the left and this integral on the right, since it's minus, become 0 because they cancel each other out. And what we have left is what's in the middle, which is x to the x plus h f of t dt. And so, for when we have h, which is not equal to 0, we can get number 2, which means that g of x plus h minus g of x over h is equal to 1 over h times x to the power of x plus h of f of t dt. Now, for now, let's assume that h is greater than 0. Since f is continuous on the closed interval from x to x plus h, the extreme value theorem says that there are numbers u and v in that interval such that f of u is equal to m, where that's the absolute minimum, and f of v is equal to capital M, where that is the absolute maximum. So m and m, capital M, are the absolute minimum and maximum values of f on that interval. So you can see here below. So here is our function f of x. We have our x, which is part of the closed interval, and then we have x plus h. And we can see that we have a value of u, and there is the minimum value of m, the absolute minimum. And then here's the value of v, and we have an absolute maximum of capital M. Now, by property 8 of integrals, we have the following. We can say that m times h is less than or equal to the integral of f of t dt from x to x plus h, which is less than or equal to capital M times h. Now we also know that m is f of u times h, which again is in between this integral, and this is capital M is f of v of h. Now, since we know that h is greater than 0, we can divide this inequality by h. So if we divide each of these three terms by h, then we get f of u, which is less than or equal to 1 over h, with the integral from x to x plus h of f of t dt, which is less than or equal to f of v. Now we're going to use equation 2 to replace the middle part of this inequality. So now we have f of u, which is going to be less than or equal to g of x plus h minus g of x over h, which is less than or equal to f of v. Inequality 3 here can be proved in a similar manner for the case of where h is less than 0. Now we let h approach 0, then u approaches x and v approaches x, since u and v lie between x and x plus h. Thus, the limit as h approaches 0 of f of u is equal to the limit as u approaches x of f of u, which is equal to f of x, and we can say the limit as h approaches 0 of f of v, which is equal to the limit as v approaches x of f of v is equal to f of x, because f is continuous at x. So we conclude from 3 and the Squeeze Theorem that g prime of x is going to equal the limit as h approaches 0 of g of x plus h minus g of x over h, which is equal to f of x. So if x is equal to a or b, then an equation 4 can be interpreted as a one-sided limit. Then theorem 2.7.4 modified for one-sided limits shows that g is continuous on the closed interval from a to b.